All right, so now we're going to move on to the last part of section 4, and this is going to be talking about the next set of concurrent lines, and it's going to be talking about an altitude. All right, so an altitude of a triangle is a segment that is perpendicular, so we know it's going to be two perpendicular segments, and it goes from one of your vertices of your triangle to a line containing the opposite side. All right, and it can happen in three different ways. It could be inside your triangle, on your triangle, or an extension of your triangle. So let me just show you what I mean. So here we have one triangle, right? And if we were to say, and we highlight this vertex, so if I want to draw my altitude, then this line would have to be perpendicular to the line opposite across them, so the side across them. So this one, the line goes through our triangle, and it just clearly passes through our side here. All right, now, another way that this could happen is if you have a triangle that looks like this. All right, we can then say that this vertex here, since this, if we say that this is a right triangle, we can say that these two, so here's our vertex, we can say that this is our altitude because it's intersecting at a right degree with the opposite side, and we can also say that this side down here is an altitude because here's our vertex, and it's intersecting perpendicular with the opposite side. All right, so in a right triangle, the two sides, the two legs that form a right angle, those are both actually, in fact, our altitude. And then the third one will be going from this vertex to the opposite side. And this point here is one of the points that we're going to discuss, right? And that's actually called our orthocenter, where all of your altitudes intersect. It's your point of concurrency, right? And then another way that your altitude can look is if you have a triangle like this, right? And I want to draw an altitude going from this vertex. Well, I can't, it's impossible for me to draw a line that's perpendicular within this side. So what you need to do sometimes is you will have to extend your side out and imagine as if that triangle has an extension, and then your altitude would actually appear outside of your triangle. So that is where the point where your vertex will be perpendicular with the opposite side. All right, so sometimes it'll be on a triangle like it was in the middle one, sometimes it'll be going through a triangle, sometimes it'll be outside. All right, and now where the three lines intersect, so where they are always going to be concurrent, and their point of concurrency is called the orthocenter of the triangle. All right, and just like with our circumcenter, it can be inside, on, or outside the triangle. So in an acute triangle, it is going to always occur inside of your triangle. So just like it did there. So there will be our orthocenter. On a right triangle, it's always going to be where the two legs come together, and where they intersect. That will always be your orthocenter. And then on an obtuse triangle, it's always going to be on the outside. So now we're going to do a quick problem, which is going to be determining if the lines that we're looking at are an altitude or a median. All right, so for this here, we have for triangle PQS, it asks, is segment PR a median, an altitude, or neither? So we're going to go over here and we're going to highlight this segment PR. Right now, when we look at PR, it's not intersecting in our triangle, so we know it can't be a median, but it does say that this segment would intersect and it is perpendicular with the extension of the side across from it. So that means that segment PR is an altitude. Right, because it is perpendicular with the extension of the opposite side. All right, then it asks for us to see what is QT. Is QT a median, an altitude, or neither? So now we're going to highlight segment QT. So now we're talking about this segment here. Well, we know it's not an altitude because it does not intersect at 90 degrees, but it does bisect that opposite side. So then we know that that is a median. All right, and then we're going to do one more problem, which is going to be on an X and Y axis, solving for the point of our orthocenter, and then there's going to be one that you'll do. All right, so now we're going to work on a problem where we're going to actually find the orthocenter. So we're going to find the coordinates of an orthocenter. So then for this problem here, first thing we want to do is we want to graph the actual points. So 0.13, 0.27, and 0.63. All right, then we're going to draw our triangle. All right, now when you're doing this, it's important to look at your triangle and see, is there any easy way for me to find an altitude? And since we have this side here that we know is a horizontal line, it is easy for us to find the altitude that will go from this vertex, from point B to the opposite side. And it's easy because the opposite side is horizontal, so all we need is a vertical line that will pass through that point. All right, so we need this line here. Now, the blue line, when it's a vertical line, we know that that is an equation of x is equal to some number. And since it passes through the point 27, we know that that blue line has to have an equation of x is equal to 2. All right, now we know that all of our altitudes are concurrent, meaning all of our 3 altitudes will intersect at exactly the same point. So if we can find one other altitude and see where it intersects with this equation, with this blue line that we just solved for, then that's where the third line will also intersect. So you do not have to find all 3 altitudes. You only have to find 2 and look for where they intersect. All right. So now what we're going to do is pick any of the other vertices. I'm just going to pick this vertex here. And now we're going to solve for the line that is perpendicular from that vertex to the opposite side. All right, so the only way that we can solve for that then is we need to find the slope of that opposite side. So that means we need to solve for the slope of segment AB. So this is point A, this is point B, and this is point C. So we need to find the slope of AB. So that will be equal to y2 minus y1. So we'll label this x1, y1, x2, y2. So it'll be y2 minus y1. So 7 minus 3 over top of x2 minus x1. So 2 minus 1, which is then equal to 4. So a slope that is going to be perpendicular to that for this purple line, that means this purple line slope will have to be equal to negative 1 over 4. That's the only way for the purple line to be perpendicular with segment AB. All right, now we need to come up with an equation for that. And we know that it passes through the vertex point C. So we know that for our equation, y is equal to mx plus b. We know our m is equal to negative 1/4 because it's perpendicular to the opposite side. And we know it passes through this point C. So we have an x and a y that we can substitute into. So that means 3 is equal to our slope, which is negative 1 over 4, times our x, which is 6, plus b. So 3 is equal to negative 6 over 4 plus b. We'll reduce that now. So that means 3 is equal to negative 3 over 2 plus b. And then our last step will be to add over 3 over 2. So we'll add over 3 over 2. So then when we want to add our fractions, we will need to multiply this by 2 over 2. So that way we have common denominators. So 3 over 2 plus 6 over 2 is equal to b. Or that means that b is equal to 9 over 2. All right, so then our equation for the purple line is y is equal to negative 1 over 4 x plus 9 over 2. All right, so there are 2 lines, the blue and the purple line. So now we want to see, where do they intersect? We want to find this point, because wherever those 2 lines intersect, I know that the third one is going to intersect in the exact same spot, because we know that the altitudes are concurrent, meaning that they'll all intersect at the exact same point. So all we need to do now is solve for this system of equations. Right? Now we already know what x is equal to, so we already know our answer has got to be somewhere along where x is 2. And now we need to solve for what y is. So all we'll do then is to substitute this 2 in for the x in the other equation. So then we get y is equal to negative 1 over 4 times 2 plus 9 over 2. And negative 1 over 4 times 2 is then equal to negative 1/2. So y is equal to negative 1/2 plus 9 over 2. And then we will combine these. So y is equal to, to 8 over 2, which then means that y is equal to 4. So we know it's at the point 2, 4. All right, since that's where these two intersect, we know that the other two are going to intersect at the exact same spot. Now, this point here does not look accurate, obviously, because I just drew a line without actually graphing for the perpendicular. These two blue and purple lines are just sketches. All right, but this is the point at which they will both intersect. So we know that the third one will intersect at the exact same spot since they are concurrent. All right, so that's it for that question. Now the last question, you guys are going to do this on your own. So you're going to send me the answers on the exact same document that you're going to share with me for the other video. All right, so you're going to solve for, determine if whether segment AD is an altitude, a median, or neither, if EG is an altitude, median, or neither, and if CF is an altitude, median, or neither. All right, now there's going to be one more video that we're going to talk about in this section, but it's kind of reviewing the last two sections because it's going to go over the 4 different concurrent lines that we've discussed.